Okay, I think we are 10 minutes late. So good morning, everyone. I'm Jun Wang, so the conference chair. It's my great pleasure to declare the opening of the 9th International Conference on Innovative Production and Construction. Next, please. This is a hybrid event, so you can attend either in person or online. So for all the online attendees, please use the chat function to comment or ask questions. And at the end of each presentation, so if you have questions, you can raise your hand in person or virtually to ask your questions. And also for online participants, please mute yourself after speaking and have cameras on when asking questions so we can see your faces. Okay, and the next. So before starting our session, I would like to acknowledge our sponsors, including Alpha Solo Tech and also the MDPI buildings. And for Alpha Solo Tech, I think they have their booth outside, maybe not in this building. I think in another building, the building 16, I think. So if you are interested in solar panels or the BIPV, you can visit their booth and have a chat with them. They will also have we will also hold an industry session, I think in this room, tomorrow afternoon from 1:30 to 2 p.m. They will introduce their latest products and also the technologies. So please feel free to join us and ask some questions or maybe share your research related to this area. So please, yeah, next. Okay, and for our conference, we have accepted 46 papers. It's very fortunate to see that the most of the construction research topics, for example, like building information modeling, the recycled aggregate, the CO2 concrete, 3D printing, life cycle assessment, as well as point cloud. All of those topics have been covered in our papers. So they will share and present those topics in the next 4 days. So please feel free to join us. And next. Okay, and we are also very fortunate to have 4 outstanding keynote speakers. Professor Xianzhong Zhao from Tongji University, Professor Kwa Le from Western Sydney University, and Professor Jack Chen from the Hong Kong University of Science and Technology. And the last one, Professor Liang Zheng from Australian National University. So they will share with us their latest research achievements and also discuss the emerging technologies such as the deep reinforcement learning, blockchain, robotics, as well as the computer vision in their talk, and also discuss the impact, of these technologies in construction industry. Okay, next. And this is our program, so you can access the full program from our conference website. If you are interested in any session, you can click the session. Next. You can click the session and then you can see the details of that session, including session chair, the online link to join, as well as all the presenters and the paper details. Okay, you can click the paper link to see the full paper before asking questions or before hearing their presentations. Yeah, next. Okay, I think this is the last slide from my perspective, and also the most exciting part about the awards. We have prepared 8 awards, including 4 best paper awards and 4 best presentation awards. So we have a committee to decide who will win these awards. And at the end of this conference, we will announce our winners. Okay, so for best papers review, I think the main criteria is based on the review comments and the review score. And for best presentations, we will have our volunteers and our the committee members to watch your presentation. So please, spend some time to prepare, and you will be the final winners. Okay, and yeah, again. Welcome everyone to attend this conference, and looking forward to all of your presentations. Next, please. Okay, now I will hand over to our conference honorary chair, Professor Xianzhong Wang from Curtin University, to give a welcome speech. Okay, hand over to Professor Wang. Thank you.
Okay. Yeah. Can you hear me now?
Yes, we can.
Okay. Thank you. So, good morning, and dear distinguished guests, and also online guests, and also my fellow Australian. And it's very pleased for me to have you here for our IPC conference, and this time in Melbourne. And also, a more exciting thing is we jointly co-event this conference with the World Building Congress. So first of all, I would like to give big thanks to Dr. Jun Wang, and he spent a lot of efforts in organizing this exciting event, and he has done all of the work, and also very good work, and so all the credits goes to him. And also, I want to thank his wife, Kadi. Kadi is also on the site, and without Kadi's support, and June cannot bring the conference to this level. Thank you very much. And also want to give a special thanks to Professor Xianzhong Zhao from Tongji University, and for him to take some time from his busy schedule to give the first keynote in the conference. Thank you very much, Professor Zhao. I guess this is, well, this IPC conference started about 10 years ago, and back in 2013. And well, when we started 10 years ago, it was mainly focused on information technology, like building information modeling and so on. And if you look at the program now, and you will find that it's very diversified, and it's more moving towards smart technologies rather than information technologies only. And we see a lot of papers around artificial intelligence, big data, blockchain, optimization, smart algorithm, and so on. And so you can see the trend is moving forwards. And the key business of IPC is innovation, obviously. And innovation, well, is really depends on it's not just a question of where the new innovation should come from. Okay, it should come from computer science, it should come from manufacturing, and so on. And it's more about a question of where in which fields in production and construction we really need innovations, and then we answer the questions related to the innovation in terms of science and development and engineering and so on. So and also I think we can well, all of you can also be the bridge between the innovation and also the engineering and engineering problems that we are facing on. So it's more about how we actually, in a smart way, to leverage smart technology to support our decision making. And I can see there's more and more roles to be played by technology like metaverse and virtual worlds and cyber worlds and so on. And we're all moving towards doing the engineering or solving managing problems from that perspective. So thank you very much for coming again, either online or offline. And I really hope that you will enjoy the next 4 days conference, not just in World Building Congress, but also in IPC. And unfortunately, I cannot be with you this time, but I will be. My heart is with you, and I will be stay online for the rest of the days. Thank you very much, and I hope you enjoy the day. Back to Dr. Jun Wang.
Thank you so much, Professor Wang.
Pleasure.
Okay, yeah, and the next. Okay, before introducing our first keynote speaker, I also want to highlight the institute, the Asia Institute of Engineering BRIN, established by Professor Xianzhong Wang, I think 2 years ago, and also by his research team. Okay, so the aim of this institute, of course, is to solve the complex industry problems by leveraging the power of the modern technologies. Okay, so if you are interested in this institute, you can Google the website. You can also scan the QR code if you have WeChat installed. Okay, scan the QR code, follow the some papers, articles published. Yeah. Okay, I will give you maybe 10 seconds to scan the QR code, and then we can move forward. Okay, next, please. Okay, now we will move to our keynote session. The first keynote will be delivered by Professor Xianzhong Zhao, and the topic is about the Alpha Trust, a MDP-based reinforcement learning algorithm for intelligent design of spatial structures. Dr. Xianzhong Zhao is a professor in civil engineering at Tongji University and the head of the Intelligent Design and Construction Research Group. So he's a distinguished professor of the Changjiang Scholars Program and was the dean of the College of Civil Engineer at Tongji University from 2016 to 2021. His research areas include steel structures, progressive collapse of structures, as well as intelligent design and construction, following his work on digital design as a research associate at the University of Cambridge. Professor Zhao has published more than 100 journal papers, has been authorized many granted patents, and served as a principal investigator of over 30 research and consulting programs both in China and abroad. Professor Zhao leads the establishment of the functional platform for R&D and the transformation of intelligent construction at Tongji University, an international journal of artificial intelligence in civil engineering, and the first undergraduate degree program intelligent construction in China. So he's the Secretary General of the Steering Committee on Civil Engineering Teaching in Higher Education and the Secretary General of the Appraisal Group of Civil Engineering for the Academic Degrees Committee of the State Council. Yeah, so let's welcome Professor Zhao to give us the first keynote. Okay, yeah, and hand over to Professor Zhao. Professor Zhao, can you control your slides?
No.
Okay. Yeah. Okay. Yeah. Okay. You need to see next, and then our IT assistant will help you to change the slides for you. Is that okay?
No, I can't control.
Yeah. Right now you cannot control, so you can present, and if you want to go to the next slides, you need to see next. Okay. And the next. Yeah. Sorry about the the inconvenience. Okay. And you can start now. Thank you. Thank you so much.
Okay. And thanks to the chairman. And good morning, ladies and gentlemen. And the presentation I give today is the intelligent design theory, methodology, and implementation, and a bit difference compared to the title listed on the program. And next page. The presentation involves 4 parts, and the first briefly introduction of intelligent design, construction, and maintenance on my understanding. Then focused on the engineering design, both by the computational method and AI-driven algorithm. Then I give the conclusion. Next. And first is the intelligent design and construction and maintenance. Next. And architectural engineering and construction is the oldest in industry and in human history, and built our dream home. And AEC industry is the backbone in China, and this year's and as of the Chinese national economy with 4.55 trillion US dollar market size, according 25% of GDP. Next. But this industry is facing big challenge, like the labor-intensive, energy-intensive. And according to the McKinsey, and in terms of industry digitization index, and the AEC is nearly the lowest business sector. And in terms of energy-intensive, and energy consumption accounts of 30% of total, and over 2 billion tons of construction waste in China in last year. And also there is some difficulty in construction under extreme conditions, especially in the Sichuan-Tibet Railway with the earthquake, harsh geology environment, and also lack of the skilled workers. Next. And to overcome this challenge, and new technology must be employed. And thanks for the Industry 4.0, that is from the Industry 1.0 and mechanization and to electrification and digitization, and finally Industry 4.0 and intellectualization. And analogous to Industry 4.0, and in 2015, and Chengdu University proposed a concept of construction 4.0, and that is, and the construction 1.0 is the prefabricated construction, and that is from the manpower and to the mechanical power to construction. And construction 2.0 is industrialized construction, and with the standard and modular construction in the assembly. And construction 3.0 and is the digitalized construction, computer-aided design and computer numerical control machine, and extend our horizontal and vertical buildings to the curved buildings. And next is the construction 4.0, we call it intelligent construction, and combining and the traditional construction technology with the information technology. And construction 4.0 originates from both technology and life demands. And considering the population in China, so the construction 4.0 and is booming in China this year. Next. And what is the construction 4.0? That is the intelligent construction. And I think analogous to the intelligence of human beings, I think, and it has the ability of perception, recognition, decision making, and cyber physical system, that is, and the digital twin has the key role in the process. For real building composite of components and drones, and perceive, recognize the change of outstanding environmental, and in the cyberspace and modeling analysis and reconfiguration, and finally, and to control the real world. And this is the loop. This is the closed loop for the intelligent construction. Next. And the traditional civil engineering has expanded and in two-dimension space, that design, construction, and maintenance and demolish in the axis of time, and material components and system in the axis of space. And click, please. Yeah. But with the CPS emerging, and we have the perception level, recognition level, performance evaluation level, and configuration and control level. And click there. Sorry. And so now, and the civil engineering and expands to the three-dimensional space. So we have lots of work to do in future, from the research and to practice and even to education. And next. There are some key technology and for the intelligent design construction. There's the digital twin. I'm sure you all know well, so I did not introduce that. Next. And autonomous perception, that is accurately and efficiently perceive physical construction entities with the ability of edge computing. This is very important for nowadays. The next. Another is intelligence recognition, and we can describe, identify, classify, and explain things by analyzing all kinds of information and using the innovative technologies such as image processing, computer vision, neural network, or machine learning. Next. And the next key technology is cognitive inference. And we want to analysis, evaluate, and predict the structure state of the project using the third generation of AI, machine reasoning, and big data knowledge reading. Next. And the next key technology is the human-machine cooperation, and make the human and machine and understand, perceive, and help each other to realize the precise control of construction system. Next. So from above, and I prefer to replace the intelligent construction with the intelligence design, construction, and maintenance. That is the IDCM. But I think path to success for IDCM lies in information and communication technology, algorithm, and scenario. And ICT and involves Internet of Things, artificial intelligence, and cloud computing, big data. And the scenario that is the Pensport scenario, and integrating and traditional construction technology with the open source algorithm. And we know if you use lots of firms use open source algorithm, and surely it has some difficulty to tackle real problem. So what we need to do and next is to develop the innovative and algorithm. Next. And next. To develop algorithms and to deal with the key technology mentioned above. Next. And civil engineering need to satisfy and safety, economy, and sustainability, and ICDM is no exception. And what's more, and ICDM should pursue and the efficiency, accuracy, and robustness. And all mentioned above is what we have done on IDCM in the past 7 years at Chongqing University. And just as Xianzhong mentioned, and we launched a new journal of AI in civil engineering. But for engineer, they prefer to talk about IDCM on by the timeline, that is intelligent planning and design, intelligent manufacture and assembly, intelligent maintenance and management. Next. Next. Yeah. So, and design is very important in the life cycle engineering project. And this is a diagram of project and effort and impact. And curve 1 in red color is the ability to impact cost and functional capability. And curve 2 is the cost of the design changes along with the project progress. From this, we can see every project decision have a greater ability to both positively impact project cost and function. The later that a decision is made, the more cost a design change will occur. And the next, click there. And AEC project, including design, manufacturing, erection, and maintenance, are jointly completed by many enterprises, not like manufacturing industry, which mostly finish the whole work and even company. So this makes the life cycle design of civil engineering very difficult. So we need to employ the computer. Please click here. Please click there. Yeah. And 40 years ago, and we used computer for drawings and structural analysis and code checking. And but it's very difficult and to do the conceptual design, let alone and the engineering design. And this is mainly because I think as the conceptual design involves in architecture, engineering, and construction, and the quantitative and non-quantitative informations, expertise, experience, and code standards in many books, and trade off any time and anywhere. And but with the development of the computer technology and algorithms these years, and some computational methods and even AI-driven design methods are proposed and make the computer can simulate what human brain is able to do. The next. There are 3 kinds of design methods and in the decision space and the performance space. And firstly is the traditional design method, and function follows form coming from the architects. And the second is the optimized design method, and form follows function to find the best design solution. And the third is generative design method, and form is function is form, and make a balance between the design decision space and performance space. And this is the computational method to do design. And furthermore, and there's some new technology this year from the parametric, it's from the computational design and to the parametric design, and even to intelligent design, and from the human machine interaction to autonomous intelligence. Next. So next, I will introduce and to kinds of engineering design method. One is by computational synthesis. The other is by AI-driven and method. Next. And analogies to human language and serious vocabulary and the grammar and to form sentences for some meaning. And analogies to this and the triangle regarding as a vocabulary and the shape series shape grammar, and we can find chart structures and different kinds of and various kinds of structures. And which one is the best? We must consider the efficiency, economy, utility, elegance, and made lots of trade-off and these factors, just as the human brain works. And by using the mathematical models, and that is the multi-objective optimization, and we can find the best design solution. And this process is just as what human brain is able to do. Next. So this method involves the design optimization, shape generation, evaluation of performance. And click, please. And the intersection area is called computational structure synthesis, and to do and structural design automatically. And there are three key technology to solve. And one is the methodology of shape generation. The second is modeling of objective and constraint. And the third one is algorithm optimization. And next. And as for the shape generation, there are three methods, and physical-based, simulation-based, and graph-based. And physical-based, in 1675, and Mr. Crook has done this test. And for the catenary line downward and reverse upward, and we can form the arch structure. And this kind of methods was widely used in dome structures, such as the Singularity family at Barcelona, and lots of domes was built by this method. And the simulation-based method and includes the force density method and ground structure method and the ESO method by Professor Xie, and also has a real project at Jakarta National Convention Center in 2011. And the graph-based and shape generation, and there's lots of this kind of method. And the key one is we call shape grammar, and proposed by Professor Xie in 1997. And there's there are three type and transformation rules, and shape transformation rules, size transformation rules, and the topology rules. And for the shape modification rules that change the location of a single joint in a design, and the size transformation rules that change the cross-section area of a single member. And for the topology rules, and I've subdivided 5 rules, and triangular dividing 2, and 2 triangular merging into 1, this kind of thing. The next. But in fact, this kind of shape grammar was employed in 1978 and by Stanley at MIT. And in 1981, and Bravery Horse in America was built using this shape grammar general. The next. And for the structure shape grammar, just as mentioned before, and Professor Christie defined planar shape grammar and shape transformation, size transformation, and topology transformation. Using this shape grammar and generate different planar charts, and the projection of planar charts onto a surface, curved surface is spatial, and we can generate a shell structure. And a planar truss and using the translate rotation and mirror, and we can generate a truss beam that is a 2.5 dimensional structure. And this kind of structure and bracing together by braces, and we can get a spatial structure covered the three-dimensional space. But this is just a pseudo the three-dimensional structure. The next. And so to make the shape grammar more efficient, and we develop rules, propose rules with form-force coupling. That is combining and mathematical modeling with the physical mechanics called geographic statics. And some professors extend the two-dimensional graphics statics to the three-dimensional space. But there's lots of limitations and in this method, such as in the statically indeterminate structure doesn't work, and for the also the structures under multiple load condition also doesn't work. So we need to So we need to propose some more simple, efficient rules to generate a spatial structure. Next. The next key problem is the optimization method. Engineering tasks are multi-objective, non-convex, and the objective factors such as strength, stiffness, as well as subjective factors. And to tackle these problems, and some optimization approaches is commonly used. This is mathematical programming-based methods and heuristic search-based methods and simulated annealing, genetic algorithm, and Monte Carlo tree search. Next. But still, there's some problems. So we need to develop an optimization algorithm integrated with engineering philosophy to search the solution space more efficiently, such as the most mathematical modeling of engineering problem with appropriate optimization variables, and developing algorithm of searching strategy from the experience of engineers and historical data. And also speeding up of the structural analysis is very important for the real design. And because the structural analysis is generally spend 70 to 80% of the optimization design. First, reference structure, and we can use the inverse stiffness matrix and to get the displacement. And the inverse matrix costs lots of time. But for the next structure generated, for the next structure generated, there's only small change for larger structures. So we don't need to get the inverse stiffness matrix of GK1. We can just adding delta X and to the former design solution, and we can get the structural analysis result. So using this analysis method, and the running time reduce averagely 70%, and makes the optimization method into a real project. Next. And next key problem is modeling of design objective and constraints. And this is the general expression of optimization model. And a matrix for design performance called cost function is formulated at the summation of design objectives and weighted constraint violations. Next. The design objective involves the safety, minimum mass, and volume, aesthetic constraint, efficiency, and design constraint involves the stability and stiffness, slidiness ratio, local buckling, and construction requirements. And but for some non-quantitative and factors such as elegance of building, it's quite difficult to give a function. Next. So, and wait, oh, sorry, next, the previous one, okay. So we tried to modeling the aesthetic of the building in the past years, and we proposed a relation function of geometric feature and using Cason's engineering. And what we know, and the aesthetic is largely depends on the intuition and experience and the user preference. The next. And so we did find some games rating people's beauty and ugly, though this may be contrary to aesthetics. And so, and we changed the rating the people's beauty and ugly to the rating the image quality, and features image blur degree, and using the CNA and the final prediction, predicting the image quality. Analogies to this model, and next, and we give the aesthetic model. That is generative randomly on the sample population and identify the possible geometric truss rules, and we got the sample with 9 factors, and by a clustering algorithm and grouped the samples and labeled the samples, and with the help of random forest algorithm, finally we gave the preference prediction model of the any truss structures. Next. Next, yeah. And the next key problem is how to modeling the constraints, because we know for structure design and lots of constraints in several books of design code, and plus the expertise experience. If we just mapping all these constraints in design books, and it's impossible to solve this problem. So what we think now is using knowledge graph and mapping this this relationship and to the constraint design constraint. This work is still in progress. And next. And using the method, and we design a real project 20 years ago, and there's this is the Paternoster Square near St. Paul Cathedral in London, and there's a wall. And next. When the sun shines, a noon mark indicates the noon for each day of the year, as compared to a sundial that continuously indicates the time of the day. And to do this, a circular disk with a hole in the center and called nodules, and cast a shadow on the wall that is marked with the plot of the equation of the time versus the declination of the sun, which was a figure of 8 sheep. The next. And this is the design requirement, and very strict, and the maximum displacement is less than 2 millimeters, and for light impedance, and the ultra diagram of the tube is less than 80 millimeters. And generally, the structure gave the traditional design. Click. Please click. Yeah, like this. But the owner think it's not good enough and not innovative. So ask us and to do this design use the computer. Next. And so by shape grammar mentioned above and generate this structure. The next. And the manufacturer in the factory and the erection on site. Next. And finally, we get the permanent get the engineering design and for a permanent structure by computational synthesis. And after that, we want to automatic manufacture and installation. And so, and to use this method, get lots of design solution and transfer the design solution to 3D printing file and 3D printing by the stereolithography. And finally, we get a real design by 3D printing. The next. Yeah. What we mentioned above is the computational method for structural design. Is the computational method is enough for automatic design? The answer is no. And because there's two obstacles. Obstacle one is we need more efficiency of engineering design. So we need reconsideration of design philosophy from the digital driven to the AI driven, and also mathematical modeling and optimization searching strategy from the experience and historical. And the next obstacle is the generation of building configuration. And you can see and generate and the structure and 2.5D, not the real three-dimensional structure, because we just give the planar shape grammar and not the spatial shape grammar. But for the planar shape grammar and the fundamental element is the triangle. But for the spatial structure grammar and fundamental element is the tetrahedron, which makes the generation as very, very difficult. The next. And so we think we need to propose another intelligent design method by AI technology. Next. There are some changes in design philosophy in terms of design in terms of thinking patterns. And the first is the traditional design method and using a trial and error process thinking pattern. And the second is the parametric design method, just programmatic way of the traditional design. And nowadays, there is a design method called intelligent design method. And this is a symmetric and intelligent process. Next. For the controlling data, we need to know how human brain works in real design. And for the structure design, and first generate some structure layout like this. Then under the performance evaluation criteria, such as subjective elegance, structural safety, constructability, life cycle, economy, and we need to do lots of trial and error process, and between this and to make the trade-off and to be manual iteration. Next. And the trade-off represented by a multi-objective optimization, and we can get the computational synthesis that just mentioned last part. But in another way, and if we think this process as the Markov decision process, this is the agent senses the state of the environment and takes actions according to its strategy, so as to change the state of the environment and get corresponding rewards, finally to get the best solution. And this process is very similar with the AlphaGo. We know alongside AlphaGo and its successor in 2016, MCT-based and agent made history by being the first program to beat a professional Go player. It is a landmark event in artificial intelligence that a machine can surpass the vast majority of people in such a complex intelligent activity, and in which the size of the solution space in Go is as high as 3 to the power of 361. And for this method and AlphaGo, we need to establish the proposed MDP model. And for Game Go AI AlphaGo, and the state as the position of black and white on board, and action set as the collection of all points to which the Go pieces can be added, and P side as the 0, 1 and probability distribution, and R side as the rewards. And to solve the MDP model and Monte Carlo tree search, MDPS, MCTS, and deep neural network was employed. The next. Similar to the Go game, and the trust layout or trust design involves node location, connection topology between nodes, and the cross-section bars. And we need to establish a trust design MDP model. And the analysis to the AlphaGo and the state side. S is the set of state, A is the set of action, and P is the transition function, and R is the reward function for the terminal state. And the 3 sequence action side of adding nodes, adding bars, and selecting cross-sectional area greatly expand to the solution space. Adding nodes, bars, and selecting cross-sectional area are quite simple rules to generate a trust structure. And all these actions do not depend on whether it's in the 2-dimensional space or in a 3-dimensional space. And so, these mostly simple rules of adding nodes, adding bars, and selecting areas, and can generate trust layout with diversity and geometric completeness. Next. And action about of the adding nodes, and until the number of nodes is equal to the max P, adding bars ends when the positive reward is received, i.e. the structure passes all the constraints. The next. And the reward function driving decision towards higher returns is designed to evaluate the action, which is based on the theory of structure geometric stability and the results from the structure simulator of OpenSys. If the structure is not geometrically stable, defined by the factoring of its structure, a negative reward of -1 is assigned as a punishment. Otherwise, and the function goes through all constraints and checks if the structure satisfies them. If this is not the case, the function receives only a reward of 0. If the structure passes through all the constraints and the function receives a positive reward. Furthermore, and the better the objective, the higher reward.
Sorry, Professor Zhao. Considering the lunch time in Melbourne, and
Okay.
you will have another 5 minutes to wrap up
Okay.
your presentation.
Okay.
Is that okay?
Okay.
5 minutes. Okay, sorry about that.
And MCTS algorithms is a reinforcement learning search technology to solve MDP problems and probabilistic and heuristic driven search algorithms, combining the traditional tree research with the artificial intelligence technology of reinforcement learning. And each iteration of MCTS process consists of 4 steps: selection, expansion, simulation, and backpropagation. And also the tree policy of default policy of state action reward. And next. And in tree research, there's always the possibility that the current best action is actually not the most optimal action. In such cases, MCTS algorithm becomes useful as it continues to evaluate other alternatives, particularly during the learning phase by executing them instead of the current perceived optimal strategy. This is known as exploration and exploitation trade-off. It exploits the action and strategy that is found to be the best till now, but also must continue to explore the local space of alternative decision and find out if they could replace the current best. And X bar is the average reward of the action, encourage the exploitation of action with higher reward, while the term is square root is to encourage the exploration of the action that are less visited. The next. And the albatross consists of 4 steps. And step 1 is the selection, and step 2 is expansion. Expand the search tree by trying new actions when new action is available. And the next is simulation, and use default policy randomly sampling action to determine the state. And the last one is the backpropagation, and given reward and update the confidence value of the parent node up to the search tree. The next. When generating a freeform truss layout, the location of the nodes and the cross-section area of the bars are generally continuous. Stage 1 in alpha truss manage these continuous variables by uniformly discretizing these variables. However, this discretization policy restricts the continuous variables from finding a better solution, and the layout obtained in stage 1 loses its accuracy to a certain degree. And to loosen these restrictions, stage 2 and the alpha truss is proposed following stage 1, and to refine the continuous variables by searching the neighborhood domain of the discrete action. And the blue dotted line represents the original truss layout requiring refinement, and the nodes and shaded by the blue square imply this node requiring position adjustment. Stage 2 of alpha truss locally adjusted the location of existing node, and amplified of each adjustment should not exceed the shaded area of the blue square. And a local subdivision grid pattern is newly generated. The next. And this is the validation of this algorithm. The design domain is uniformly discretized into 17 times 9 grid pattern, and 3 series steps for adding nodes. H for adding bars and 8 for selecting number size as depicted in the red 3-column figures. Next. And the stage 2 of alpha trust is used to refine the layout obtained from the stage 1 without changing the connection between the nodes. And the refinements are conducted by 25 rounds. And the weights of the structure after all rounds of refinement are presented in the trust weight versus number of rounds in the figure. And the results show that the rate of decline in the weight gradually decreases after several rounds of refinement. After the first 10 rounds of refinement, the original weight is decreased to 1455.62 kilograms and is reduced by 17%. The final weight is only 83% of the original weight. This implies the refinement to produce a 2.8 decrease in the weight after the 10th round. So this is the validation from a 10-bar benchmark test. And this is the design requirement and the design constraints. And this next. And this is the result. And you can see in the figure, and red and blue color denote the tension and compression bars respectively. Comparison between the results from alpha trust and those from previous studies is given in the table, and verifying the validity and the efficiency of the alpha trust. And the next. And this is a tree-spike design of a non-mark cantilever introduced before, and the quite same conditions. The latest design solution is only 37.2 kilograms, whereas another solution with more aesthetic appearance with 41.6 kilograms. The next. And compared with the design solution and by computational synthesis mentioned above, and this method, the weighting and the trust weight is 77 kilograms. And we can see the AI-driven design in the red columns and get a better solution. Okay, that's all. So the conclusion, yeah. The next one. So the final pursuit of civil engineering is the efficiency and value, and intelligent design, construction, and maintenance is one of the most important means. And intelligence design is one of the crucial parts of IDCM. And from the traditional design, parametric design, and to intelligent design, such as alpha trust and modeling the trust design as MDP model, and proposing the artificial intelligence technology to solve the design. And in the future, we need to keep on developing innovative algorithms to make the IDCM more accurate, more efficient, and more robust. Thank you very much.
Thank you so much, Professor Zhang. Professor Zhao, from your presentation, I think we can clearly see the evolution of the structured design from the traditional design to parametric, or the computational, and now it's the intelligent and generative design. So we can, I think we can take 1 or 2 questions. So if you, for the audience in the room, if you have any questions, you can ask now. Any questions from our audience? No, I know most of you are from construction management background, but you can think about the intelligent construction, okay, about the construction scheduling, you know, from the traditional scheduling to the parametric driving scheduling. And now I think some more researchers, they try to to do the generative scheduling. So by using the same methods, shown in Professor Zhao's presentation. And maybe one question from my side. Professor Zhao, can you hear me?
Yes.
We all know that maybe in the future, the artificial intelligence will take over the structure design. So any suggestions you can give to our current structural engineer students so that they can they can prepare and for their future career?
Yeah. And I think for the students, and the basic principle is very important. So in university, and they need to grasp the basic principle from the mechanical to the structural design principles and construction principles. And after that, and we can do a lot of practice, and especially in the multidisciplinary, and this is very important in the future, because the solo work, design work, must be replaced by computer in maybe the 5 years. But for the whole process of the system, and combining lots of and interdisciplinary knowledge, and cannot be replaced by a computer, I think.
Okay, thank you, Professor Zhao. And I also want to highlight the journal, the AI in Civil Engineering. That journal, I think Professor Zhao is the editor-in-chief, and it's a new journal. So if you have done some research in this area, very welcome to publish your papers in this journal. Okay, thank you again.
Can I ask a question?
And welcome to submit your original work and to this journal.
Yeah. And then the question from our online audience. Okay. So
and Xiang
yes,
is also associate and chief editor-in-chief. Yeah.
Yes. Yeah. That's well, that journal is a very good one, and also I think it's a very timely journal that our area quite needs. And so, Professor Zhao, thank you very much for your presentation, and the keynote is very exciting. And I just want to ask a question, which is how much do you think our industry views the artificial intelligence in design and also probably in construction? So what's the views in well, at least from China industry, how they see the trend and how they see the deployment of the technologies in their industry?
Yeah, and I think for the structural design, and in the using computer to analysis and code checking, and is well done. And for the parametric design, and I think some and big design office has done well. But I think in 2 or 3 years, and parametric will be the normal design method in China. And but for the intelligent design, especially for the autonomous design, intelligent design, there's a long way, because the constraint and design objective is very difficult to modeling. So for that, I think a long way, at least 5 to 10 years. And but for the construction using artificial intelligence on construction site, and I think for some specific task, such as counting the number of steel bars and the diameter of steel bars, and this kind of thing, and nearly 1 or 2 years, and we can achieve a lot in this area. But for the general artificial intelligence work, that means and combining and different task work, even too, there's also a long way, and combining 2 specific tasks, maybe 2 or 5 years. But if we're combining and 3 or more tasks together and needing a long time, this is mainly because the difficulties in optimization and programming of the construction process, I think.
Yes, thank you very much.
Okay, thanks again, Professor Zhao, for your time and your great presentation. And also, thank you, our honorary chair, Professor Wang, and thanks our IT assistant team, and also our volunteer, Alisa, right? Okay, yeah, thanks for all of your support. And I will close this morning session, and it's our lunch time, and see you all in our afternoon session. Yeah, thank you. Thank you so much.
Thank you.
Thank you. Thank you. Bye bye.
Thank you, Wenjun. Thank you. Bye.
Yeah, thank you. Bye bye.
Yeah.
Thank you. Thank you all. Bye bye.
Thank you.
Bye bye.